All right. Sorry, I'm a few minutes late. The doctor called and I had to wait to get an appointment scheduled. And then to make it worse, I have to leave 5 minutes early. so let's jump in. All right. So last time we finished writing our ROT 13 related to shared memory, right? And I introduced the idea of message passing, and we're going to look at that through something called message queues today, and then we'll have an assignment to effectively do the same ROT 13 thing over message queues, which won't be very difficult, and we're going to kind of look at the pros and cons of message queues here in a second. Some of this is a little bit in broken English because of where I got it from, but when you read it through the slides, but I'll actually give a new version of this. When to use shared memory. So at the high level, the difference between the function, let me make sure am I sharing my screen online? Yeah. And I'm recording. So at the high level, we want to think about the difference in how shared memory versus message queues works from a problem-solving perspective. Who cares how they work under the hood? But from a problem-solving perspective, shared memory allows you to write something to a common place in memory and potentially leave that value at that place in memory to be read again later or by other processes, right? We are not, we do not have to lose the message if we don't want to. Now, we saw last time that we had that one line at the end of our read function that will destroy the shared memory if we want. So we could receive our message, then kill it off so nothing else can read from it or whatever, if it was a top secret message or something like that. All right. So if we need data, so we might say, if we need data to persist, shared memory might make sense. It's not the only way to do it because you could pull off persistent data with message queues, and we'll see that here in a few minutes. But generally speaking, if we want kind of the go-to move to be the data persists, we would use shared memory. With that in mind, though, what's the problem with shared memory? Shared memory, let's say, but it dictates that we come up with some kind of protocol to acknowledge road rage. Some sort of protocol to acknowledge when messages have been put into the shared memory. All right, so we get the benefit of persistent data, but we have the cost of now we have to kind of micromanage how that data is going to be used by one or more processes. And we can imagine the more processes you have using that data, maybe the more complex that comes. So it's almost like if you're watching a baseball game or something like that, the third base coach is giving the steal signals. He's going pulling on his ear and all sorts of stuff. So you have to come up with some sort of mechanism for communicating across shared memory, where maybe it would be nice if I want to think about message queues. This other thing is kind of like a bulletin board. So when you're in the hall, and let's say you're looking for apartments, you might go up to an apartment listing bulletin board, and people have they pinned up a bunch of stuff on there. So maybe there's like apartments in Cedarburg, apartments in Grafton, apartments in Mequon, something like that. So you would go and you would look under the Cedarburg ones, and you would see an apartment listed there. The difference is that in real life, you could walk away and leave that thing in place, right? But the way a message queue works, it's a queue. So things get added to it, and it's a last in, first out. It's a line, just like at McDonald's or something. So the first apartment that was listed under the MEC1 category would be there. And if you went and read from that, that apartment is now gone. You took that apartment. You have that information, and it does not persist. You can always put it back at the end of the queue. If you say, I'm not really interested in it, so I'll just put this back on there, so maybe somebody else will eventually grab it. But data does not persist. So we'll add a similar slide. When to use message queues. When data does not need to be persistent, but data, let's say, benefits from being categorized. So we can have different kinds of messages. You know, we can have, in my example, I have like a message type 1, a message type 2, so on and so forth. So if I went and I read from a message queue 3 times, and I read, you know, Grafton Apartments 3 times, I would be removing entries from the Grafton apartment queue, but not necessarily from the Cedarburg or the MEC1 apartment queue, because those would be different categories, and that could be beneficial, right? You know, we can imagine if you're having multiple processes talking to each other, you could kind of have almost maybe a two-way communication, right? Maybe when I send you a message, I categorize it as type 1. When you send me a message, you categorize it as type 2. So whenever you're reading a message from me, you always grab from the queue that's 1. When I'm reading a message from you, I always grab from the queue that's 2. So now we can have two-way communication, and we don't necessarily have to worry about whose turn it is. Maybe every 2 seconds or something like that, we go back and we check the queue to see, is there anything new? All right, so we can say there's some still inefficiencies from that perspective, where I kind of have to keep going and checking the queue, checking the queue, checking the queue. But at the very least, I'm not preventing you from writing something to me, and you're not preventing me from writing something to you. All right, that makes some sense. So we can maybe give an example. 2 or more way communication using different, what do they call it? I think they're called message types. So maybe call these queue labels, where each queue is independent of the other queues, but they still all operate as a queue, where an item is removed when it is read. All right, you get that difference between those? So you might even say that shared memory is kind of a generic solution that gives you a lot of flexibility without any sort of structure, whereas message queues is a more evolved solution that gives you a lot of structure, less flexibility because of the nature of how it works, but at least now as problem solvers, we kind of know where the constraints are. This is how it works. I have to solve the problem in terms of this, but it's already given me some conveniences that maybe allow me to accomplish some common type of communication between processes, something like that. Think about maybe a merge sort using message queues, where you have the top level process that has your data. So it puts the data out there, maybe on, message type 1. And then other processes come and check in, and message type 2 and 3 have their subsorted data. Then you ultimately can get the stuff built back up by having your final version maybe message type 12 or something like that. You can kind of have this break up communication and then bring things back. You can even if you want to do it based on like who's ready for work next, let's say you have 10 workers, 10 processes that are all working on a problem. And what you can do is you can assign each of them a modulo ID. So it would be, any message so the first message the first guy would read would be message 1. The next message for him would be message 11. The next message for him would be message 21 from that queue. Okay. Or because queues, you read from it, you can always write to that same queue to talk to that guy. Is there more work? So you can have one person who's handing out work. So you're going to give worker 1 work, worker 2 work, worker 3 work, worker 4 work, worker 10 work, worker 1 work, worker 2 work. And all it does is just stack up on their queue. Well, I don't want to say stack up on their queue. It gets in line in their queue and in queues in their queue. So whenever they're ready, they can come back and get their next assignment, something like that. All right. All right, so sending and receiving process, we'll see a code example here in a minute, but effectively we have a module that works in the operating system. So it's a module in the operating system that knows how to handle message passing. Okay, it does the magic for us, and somehow it creates this message queue. For all we know, it's using shared memory. It's using sockets to connect these two together. Who knows? It doesn't matter what's under the hood, right? That would be an implementation specific thing. All we know is, hey, I want multiple processes to be able to share information. And if I want them to play by the rules of a message queue, I can do this. Now, a couple of these functions we've already seen. So we've seen this generator for generating unique key. We're going to use that with shared memory. We're going to use that for other inter-process communication. All right, so this guy is a random number generator that gets us a unique ID on the computer. All right, so then our MSG get returns a message queue if it already existed or creates one for us. And you'll see that by an example. Then we have the two fairly self-explanatory ones, right? Send something to the queue, read something from the queue. But the difference here is that when we send, not only are we sending a message, we're also sending a type. This is for worker 1. This is for worker 2. This is for message 9, message type 9, whatever. And we could just make them up to our heart's extent. Probably the size of int is, I'm guessing. It might even be long. Probably is a long. 2 to the 64th. So we could have a lot of unique message types if we'd like. Receiving, same thing. We ask for a message given its type. All right, and I've set up our example to kind of show this. All right, and then this last one, I think we've actually seen this one before. This was the same thing that we used to delete shared memory when we were done. It would also be the thing that you could use to delete a message queue when you're done. If you're just saying we're done using this guy. But our bread and butter here is really these two guys for all communication, and then this guy one time per program to get per process to gain access to that queue. All right, so let's go look at some of this code over here. And hopefully I left it in a working state because I was finishing up while I was on hold with the doctor. I had it in a working state. I just added some stuff to it. I'm pretty sure it works. All right. But we'll see here. All right, so we're using a lot of the same stuff we used before. We're still using our inter-process communication, but instead of our shared memory library, we're using the message library. Okay, this value max, this is the number of bytes for the maximum size that I set for whatever string you read it. You can make it whatever you want. The larger that is, the more space it'll take up in memory. Who cares? All right, now messages that are sent get stored inside of a struct. Because I mentioned that a message is stored as a string with a corresponding type. Okay, now this isn't the way I like writing strings, but I grabbed this off of an example thing, so that's how they wrote it. So we're getting to see lots of different versions of stuff here, but our struct type here is called a message buffer, and it holds the type of message, which is a long, and then the message itself, which is a string. All right, and this guy right here just goes ahead and creates a variable of type struct message buffer called message. I actually created another variable of that type below. All right, so then we're gonna get our key just like we did in our shared memory. So we get our, we have a string associated with this, as we just called it prog file. So whatever you want your bulletin board to be called, you can name it whatever you want, just as long as all of your participating processes know that string. That way they can get the that unique identifier. Okay. Then we'll go ahead and get our message queue. Given that key, given its read and write for everybody, and we are masking it with IPC create, just like we did before. It says created if it doesn't already exist. All right. Now, initially, I'm setting my message. Remember, that's my variable right here that was created. That's of type message buffer struct. I'm setting my message type to a 1. Later on, a couple lines down here, I write to a message type 2 a bunch of times. So we can kind of see that queue build up. All right. So I'll set my first message to message type 1. And then I'm going to go ahead and I'm going to write some data. So well, it's asking what data do you want to write? So really, you know, what do you want to write? Is really what we should ask there. This is another, this is a stream reader. So fgetS reads in a string from some stream. Could be a file stream. In this case, the stream I'm using is standard input. So I'm reading a string of maximum length max, which was my macro from up here. So a string of maximum length max from this input stream, standard in. It could be a file, it could be anything you want, but in this case, it's a standard in, which is defined inside of standard io.h. Standard in is the keyboard. It's built into the operating system. Okay, so read a string in of max length from standard in and store it into the message text portion of my message struct as a string. All right, so now I've packaged up this structure with 2 things: the message type, which is 1, and then the text for that message, which is the string I just read it. And then what am I going to do? I'm going to send that message given the message ID. So that's the unique identifier for my bulletin board, for my message queue. And I'm going to pass it the address of message here. Why do you think I'm passing the address of message?
Smaller to pass.
Okay, that's definitely true. Okay, smaller to pass because a memory address is smaller than presumably a string plus an int or a string plus a long, right? Okay. What capabilities would I have inside of message send if I passed in the address of a struct? What could I do inside of message send? Not necessarily that it does it, but what could I do inside of message send if I'm passing it the address of that struct? Yeah, make changes to it. Because structs by default are passed by value. In this case, I'm passing the struct by address for the reason of size, right? The address of a struct is likely smaller than the struct's physical weight, if you will, okay? Because a struct otherwise would be passed by value. This would allow message send to change that struct if it wanted to, but I do not believe it does. Because what's going to happen is on the other side, it copies the contents of that struct onto the queue. That struct isn't important from that point forward. I actually did create new structs down below. We'll actually be able to test that idea when we go through this, but we'll just have to move one line. But in any case, that's the rationale for why we're passing in. Well, first of all, the function requires that, right? It says it wants a struct pointer, not a struct. But the rationale behind that is an address is smaller than a struct itself. So with that in mind, when I say size of message, what is the size of message here? What kind of animal is message? So here's message. It's a variable of type struct message buffer. What's the size of this guy? When I'm passing in size of message, is it the size of that memory address or is it the size of that struct? Probably the size of the struct, right? So this struct is size what? Char pointer, which is 8 bits, 1 byte, and along, presumably 64 bits, 8 bytes. So this is 9 total bytes, plus any overhead that structs require. Will actually be interesting here real quick. Let me, I'm gonna do printf %d \n size of message. I'm interested to see what that value is. Then let me comment out the rest of this stuff for now. Long unsigned int. Well, actually, we'll fix it on this side. You're an int now. $112. So that is actually it's 112 bytes. Actually interesting. Reason for that is 100. It gave you the full size of this char array. Plus 8 is 108, plus presumably 1 more byte. No, 108 plus 4 bytes memory address of the struct. So if I had changed this to a char pointer, which would not initialize it, but the way we're reading in here should be fine because we're using fgetS to read into a pointer. I think that should still work. Now I'm guessing this will be the 8 plus 1 is 9 plus 4 is 13. Didn't allocate memory for it. Let's see if I can, but if I come in and I allocate memory manually afterwards, and I say something like message dot message text equals malloc 100 of type char pointer. Now it's allocated, so I should be allowed to put stuff there. I think it's still gonna, I think it's gonna be back to the 111 or 112 based on, because my understanding is this is syntactic sugar. Well, the other thing is syntactic sugar for this. It still allocates the memory. So I think this memory will get sucked into the scope of this struct and then be part of the size of that struct. Standard lib. Oh, that was the 16. So that's, what do we say? 8 plus 4 is 12, plus 4 is 18. Where's the 16 come from? How long is 8 bytes? Or did we do our math wrong on the other side when we added it up? So before we had a bucket, we had 100 bytes plus 8 bytes is 108. Plus 4 gave us 112. That was the number initially, right? 112. So this one should be 1 byte for our char pointer, plus 8 gets us 9, plus 4, which is 13. Oh, no. A char pointer is 4 bytes. It's the size of a memory address that happens to have a char living there. So that would be 4 plus 8 plus 4 is 12, plus 4 is 16. That gets us the right math. So let me show you what I just said there. Relatively inconsequential, just kind of connects all these dots since we're messing with memory so much. Message text holds a memory address. So the size of this guy is 4 bytes, the size of a memory address, even though a char is 1 byte. A char pointer, a variable capable of holding the address of a char, is 4 bytes. So 4 plus 8 bytes is 12, plus 4 more for the struct gives us 16. Whereas before we had 100, right? It gave us the full footprint of that because it was a char message text 100. So message text was an array that has 100 bytes of memory associated with it. And this then gave us, so in that case, this should give us 100 plus 8 plus 4. So that's 112 in that example. Actually pretty interesting when you consider the difference in size between those using, that raises all sorts of questions about the efficiency of this behind the scenes.
Is there any benefit to doing it the 112 bytes way?
Convenience. My short version answer to that right now is convenience. It's cleaner to write than to do this and then allocate memory, or feels easier to write. But I can't think of any reason historically when memory was at a premium. So yeah, I'm going to say no. We could experiment with it a little bit here. The rest of this I think should. Oh, the rest of this did work. It read it in because we got our size of it, right? All right, so now I'll go ahead and uncomment out the rest of this stuff. All right, so we read in our string into our message text. Now what's interesting here is that if the maximum size of our string is max, why would we necessarily allocate 100 here when we allocate max? That's the most it needs to hold is max, so we should be more efficient. But I'm just arbitrarily choosing value of 20 bytes for max here, but We can change that however we want, but that's the point of a macro. We change it here, it'll automatically change here, it'll automatically change it down here. So reading our message into our struct, send our message given the ID, this is like the location of the bulletin board, the message queue, pass in the address of the struct, and then pass it the size of the struct in its entirety. Okay, this is going to tell the other side how to read from that guy, presuming they start at this as the base address of the struct and want to read all the way to the end of it. This, between these two, it gets them the entire memory footprint of that struct, even though they should be able to work with the struct through normal struct syntax by saying, let's say on the other side, it's called, I don't know, message struct or something like that. They should be able to say star message struct, and now they have the actual struct that they can then say dot message text or dot message type to get those pieces. But I suppose since it's requiring the size of it as well, you actually could find out how big this guy actually is. This is where it starts, base address. This is the number of bytes until you reach the end of it. All right, so this sends our message. Then I'm just printing out, this was the message we just sent, evidence. Okay, so that will send that one message. So let me start with just that. And that'll put it onto the message queue. So we can go ahead and do this and run that. All right, so we'll put woot onto the message queue for bucket 1. Okay. Now let's go over and look at my reader over here. Very similar setup up top, and heck, we'll just leave it with this syntax here. Hopefully we're getting to the point now where bouncing back and forth between all these different syntaxes is all seemingly like the same stuff. But we just saw it actually isn't the same. This is pretty inefficient, relatively speaking. So we'll get our ID for our, this is our actual message queue. We have that. I have this variable here for my message type because I'm reading some stuff in here. Right now, we know we'll only have something written to message type 1. Okay, so the first thing it's going to ask us is, what is the message type that you're retrieving a message for? It's like an answering machine type thing. Okay, so we'll go ahead and read in. So message type is a long. What do you think %LD means? For my placeholder. Decimal. Long decimal. This is a long decimal. All right, so we're going to scanf. Scanf takes in a format, and it takes in where we're putting it. So we're going to read in a long decimal and store it into the address of message type. Why are we putting into the address of message type rather than message type itself? Because message type is passed by value by default. It's not a place, it's a value. The place is the address of message type. That's where we're reading this value and placing this at this location. Does that make sense? This is how scanf works. It's an older function. It's not read this thing into this value like we used the scanner in Java. You know, we have int a equals scanner next int or something like that, right? Well, this is saying, look, you want me to read something in, and the thing I'm reading in looks like this. It's going to follow this pattern of a long decimal. That's it, some long decimal. And where do you want me to put it? In computers, the where at the end of the day is always a memory address, right? Other languages abstract that from us by saying, oh, look, if it's an int, just say that int equals this value, and I'll do the stuff behind the scenes for you. I'll make it work. But using a very old library like standard IO with scanf, it says, look, if you want me to put this in a certain place, you tell me the place I'm putting this, the address where that variable is. All right, then we're gonna just print out message type. I was proving I was reading this incorrectly. So we don't need that right now. And then we'll go ahead and receive a message from our queue. Here's our queue. Where we're receiving it into our message struct that was defined up here. Okay. But in this case, we can say, well, why are we passing it the address of message? Well, probably two reasons. One, it's smaller than the size of the struct itself. But more importantly, in this case, they are going to put my answer in here. They need to be able to write to get this back to me. Okay, we're not returning a value here. The answer gets placed in here. This guy probably returns an int just like every other function does with interprocess communication in C. All right, so we'll pass in the address to that struct, the size of the struct, and also the message type we're requesting. So it makes sure it grabs it from the correct channel at that queue. All right, and then I'll just say, hey, the data we received was the message text from that message that they presumably wrote to here in memory. All right, so I'll go ahead and compile this guy. And we'll run this. Now, if I type in something other than 1, it's going to go and try to read from a queue that doesn't have anything in it. So if I type in a 2, I get nothing. There's nothing in there. If you want to wait, maybe somebody else will write to it and I'll give it to you then. But right now it's blocking, correct? My program's sitting here blocking. That function hasn't returned. The message received hasn't returned. I'll go ahead and run this again, but I'll type in a 1. fgetS must not work well with char pointers. I think it's pretty clear right in something, and it probably used to be woot for the sake of time. But now notice I'll run this again. I haven't recompiled the other thing. If I say channel 1 again, it'll give me nothing. I did remove it from the queue. Okay, it did not persist. So let's go and run the original one again. So now we'll write out woot data set was that. I'll compile the other one, run this again. So there's my woot. I'm sure we can get the other thing working. It probably just, we wouldn't use fgetS. We'd probably use another function, maybe probably use Scanf, and that would read it into a memory address correctly. Now for the rest of this part over here though, open up Slack, I guess. Just to prove that persistence thing, I had a loop in here. And this is the part I haven't tested yet, but let's just assume it's perfect. So I go, well, I guess we're going to find out. Are you going to bet against me, Brocker?
Everything you say.
I tell my wife that too. I get the eye roll. All right. So for int I equals 2, I is less than 10, I plus plus, we're just going to do this 8 times, right? So what I'm going to do is I'm creating a struct here. And what I said before is we could test this. So each time through this loop, I'm giving myself a brand new struct. So I'm not relying on it, on the other guy not taking that value, you know, because we're passing in the address. And so I'm making the assumption here that when I pass in the address of the struct, they might not copy the values out of the struct. They might store the address of this struct. Because of that, I'm just going to guarantee I always get new addresses. I'm going to create a new struct every single time through this loop so that when I write the address of temp, it's going to be a different address each time. And we'll be able to test it pretty easily to see if that was required or not by just moving this outside of that. But let's run it this way first. So I'm going to do something 8 times. What am I going to do? I'm going to print to a string. What am I going to print? I'm printing into temp's message text a string followed by a number, a decimal. So I'm going to say hello 2, hello 3, hello 4, hello 5, hello 6. All right. And I'll set the message type to always 2. So I'm writing it to the same message queue over and over and over again, multiple messages, 8 of them. And then I'll send the message. All right. So we see right now our queue is emptied out, right? So let's go ahead and run our writer. So I'm going to still write woot to Q1, but then I'm going to write the hello 2, 3, 4, 5, all that stuff to Q2. All right, so there's my woot, but that other stuff did happen. So now I'll do my reader, or at least it compiles. All right, now I can go ahead and check on 1 if I want, and that should give me my woot. If I go back in, I check on 1 again, there's nothing there. If I go back in, I check on 2, it should give me my hello 2. It's a queue, not a stack. There's my hello 2, hello 3, hello 4, so on and so forth, right? Last thing to test to close our knowledge loop here is, will this break? I don't think it will. I would be very surprised if it's storing, when it hands off to the, oh, I actually wouldn't be surprised. If it hands off to a queue, is it storing the address of the struct, or is it copying the elements from the struct over to the queue? Really, the queue does not need to store the type. Once we know the bucket to drop the string into, we actually only need the string, right? So if I'm putting something into Q2, I don't need to say, here's a struct for Q2 that I'm going to shove into Q2. All I need to say is, the struct tells me I'm putting this into Q2. Find Q2, take the string, drop it into Q2. And chances are, because I'm removing it from the struct, I'm going to go ahead and do like probably an sprintf or something like that to write that string into there, so it'll be a different memory address. So this should work. I shouldn't have to recreate temp each time. I'm really just changing the contents of temp each time, which actually means I should be able to hard code that guy to a 2 just from the very get-go. All right. So reader doesn't need to change, but our writer. Actually, we left 4 things in our queue. So the next thing we're going to read out there is hello 5, hello 6, hello 7. Okay, so let's go to our reader. So we have a woot back in there. There's our 5. There's our 6. There's our 7. There's our 8. Next one should be a hello 2. Oh, I wanted the 10. So there's 8 things, 2 to 10. 2 to 9, less than 10. So there's our hello 2, hello 3. Yep. So it does copy the contents of that string out. And we should be out of stuff now. All right, see how the queues work? All right, so quick homework assignment for you to practice with this. Make your ROT13 program work with message queues instead of shared memory. Okay, I'll go ahead and push this code up. All this stuff is still inside that ROT13 messenger file folder. I just have, what did I call it? I think I called it writer MP and reader MP for message passing, because the other 2 things are still in there. All right, questions, comments, concerns, bribes. All right, I will see everybody on Monday.